Welcome to Heated Materials Lecture 11. In the last lecture I looked at relationships between dimensionless numbers for flow-through pipes and free convection, and of course these were ways of then allowing us to calculate the convective heat transfer coefficient H. I also looked at boundary layer thicknesses, and then I finished this session by looking at the semi-infinite solution limited by convection. I want to continue to talk about systems where convection is important, and basically I want to look at the cooling of a section. First of all, I will do this in the context of lumped heat transfer, which we've already looked at, and then I will go on to the what's known as a Heisler chart solution, which, unlike the lumped approach, allows you to determine the temperature gradients in the body that you're dealing with. So I'm going to do this in the context of strip casting, and I'm going to do it specifically related to aluminium strip casting, where we can say that convective cooling is the dominant term. It doesn't mean there's no radiation, but convection will be dominant. And of course you can always incorporate radiation in a simplistic fashion by assigning a radiative heat transfer coefficient in terms of the convective one. The system I'm going to deal with is a strip of aluminium alloy 6 mm thick by 150 mm wide. Say that its temperature on exiting the rolls is 200 centigrade into an air temperature of 20 centigrade, and the strip is moving at 1 meters per second. And I'm going to ask, what is the temperature of that strip 10 meters from the roll exit, in other words 10 seconds after it's left the rolls. And I've given the relevant thermal properties of the material and also a convective heat transfer coefficient of 20 watts per meter squared per Kelvin. So I'm going to ignore conduction along the strip and consider what happens to a slice of material. And in doing that, the volume of my slice therefore is given by the cross-sectional area times some unknown length L, and the surface area likewise has to be expressed in terms of the unknown length L. But of course when you then check whether you can apply the lumped solution, the HV over Ka term, the L's cancel out, and we can clearly show that this gives a value that's much less than 0.1. In other words, the lumped solution will apply to this problem. So, as I've already said, for a 10 meter distance, that means that 10 seconds will have elapsed, and putting all of this together into the lumped solution, again the L terms in here will cancel out. I end up overall with a temperature of 195 centigrade. However, this approach of course does not give any information about the temperature gradients within the material, and so for example, if we wanted to know what is the actual difference between the surface temperature and the center temperature in this case, the approach I've just used is not going to give an answer, although of course because we were dealing with aluminium, which has a high thermal conductivity, the difference will actually be quite small. However, what I want to do now is to develop a method which would allow us to work out what that difference actually was. So I'm dealing with a thin continuous strip. Essentially it's a finite thickness plate, the thickness 2L. I'm going to assume for the moment that it actually extends indefinitely in the other two directions. Now clearly in the direction of travel that is essentially true. It's slightly less true perpendicular to the direction of travel, because we've said the strip has a finite width of 150 millimeters, but compared to 6 millimeters that's still effectively infinite. And it turns out the method I'm about to develop can ultimately be applied to things that are finite in all three dimensions, but it is easiest to start by considering it being finite in one dimension only. If it's finite in one dimension only, we have a 1D problem, and I can basically say that the rate of change of temperature with time will equal alpha, the thermal diffusivity, times the second partial differential of the temperature with respect to distance through the thickness. Once again, I'm going to define a dimensionless temperature, which is in terms of the far field temperature and the initial temperature of the object that we're dealing with. So I can re-express my equation as partial d theta by dt equals alpha partial d2 theta by partial dx squared. Again, I'm going to assume that my solution can be written as a product of a function based on time and a function based on distance. So that, in other words, theta equals tau of t times x of x. And if I do that and substitute this equation into this partial differential equation, I end up with ultimately two differential equations, one in terms of tau and time and one in terms of capital X and distance. Those two equations are equal to each other and then equal to what we call a separation constant, just as we did with the Fourier series before. In this case, I've called the separation constant minus a squared. This again reflects the fact that I already know the form of my ultimate solution. Strictly, I can just call it any arbitrary number I like. But clearly, these things do have to equal a constant, because the first section here is purely dependent on time, the second one is purely dependent on distance, and for them to be equal, they have to be equal to a constant. Taking those equations, rearranging slightly, we have two differential equations, d tau by dt plus a squared alpha tau equals 0, and d2x by dx squared plus a squared x equals 0. The latter of these two equations, again, should be familiar as being the equation of simple harmonic motion. The left-hand equation is actually very simply solved by bringing all the terms in tau onto one side, the terms in t on the other, which initially gives you a log function, or rearranging an exponential function, that tau equals some constant times the exponent of minus a squared alpha t. The right-hand equation, as I said, is an equation of simple harmonic motion. Therefore, standard solution of that, it says that x equals some constant times sine of ax plus another constant times cos of ax. Thus, my general solution is theta equals the exponent of minus a squared alpha tau, some constant times sine ax plus another constant times cos ax. d1 is equal to c1 times c2, and d2 is equal to c1 times c3. Now, for the case of a strip at an initially uniform temperature, then we can say that theta of any x and time 0 equals 1. And if we assume that there is uniform convection of both surfaces, although of course in the problem that I've already set out, the top and bottom, you would expect to be strictly different, because free convection relates to fluid flow arising from density changes, and the hot air above the top surface were able to rise more easily than the air that is beneath the strip. But we'll assume for simplicity that it is a completely symmetric situation. Then the boundary condition under those circumstances will be that the heat flow out of the strip given by Fourier's law equals the convective loss given by Newton's law of cooling. So we have minus k d theta by dx equals plus or minus h theta. Plus minus just indicates that we're dealing with the top surface and the bottom surface. And x equals 8 plus or minus L. Putting all this together, at t equals 0, the dimensionless temperature at the top surface and the bottom surface are d1 sine AL plus d2 cos AL for the top surface, and minus d1 sine AL plus d2 cos AL for the bottom surface, because the sine of minus AL is just equal to minus sine of AL. These two statements can only be generally true if d1 equals 0, and in other words our solution immediately reduces to the dimensionless temperature theta equals the exponent of minus a squared alpha t times d2 cos ax. We can now differentiate that to get d theta by dx, and that will just be equal to minus a exponent of minus a squared alpha t d2 sine ax. Thus, applying boundary conditions gives us two equations which are essentially identical. The top surface where x equals L, we get Ka exponent of minus a squared alpha t d2 times sine AL equals h times the exponent of minus a squared alpha t d2 cos AL. On the bottom surface there are a couple of extra minus signs, but of course they will cancel out to give exactly the same equation. And also, of course, in both equations you have on the left and the right hand side the exponent of minus a squared alpha t. So those terms will cancel out, and thus overall what we'll get from this equation is that Ka sine Al equals h cos Al. And that can be arranged very simply to give us Ka over h times tan of Al equals 1. It's convenient at this point to multiply both sides of the equation by L and also define a new term beta which is equal to Al. So doing that in two steps, we first of all get KALH over times tan Al equals L. The term Al we're calling beta, hence we get tan beta. Al here becomes beta, and then the other thing is I've cross multiplied the h and the k, so this would give on the right hand side HL over k, but that is just the bio number which we previously defined. Now this equation has a number of roots, so here I've shown for the bio number equals 0.001 the first four roots of the equation. On the larger graph you can't actually see that it does cross the axis, but here you can see it does cross the axis, so this will be the first root, and then which we call beta 1, then beta 2, beta 3, beta 4, etc. You get a similar looking graph if the bio number equals 0.1, but you'll notice the intercepts are at slightly different points. But essentially these graphs just show how those roots change with the bio number. And each of those roots of course corresponds to a valid solution, and just in the same way that we did with the Fourier series solution, we have to sum all of those valid solutions. So we now have a constant that corresponds to each value of beta I, and the overall theta equals the sum between I equals 1 and infinity di times the exponent of minus beta I squared alpha t over L squared times cos of beta I x over L. And we now need to evaluate the di coefficients, and we go back to our original boundary condition that theta equals 1 at time t equals 0. So the expression at the bottom of the slide simply states that, because exponent of 0 will give us 1, so we just end up with di cos beta I x over L equals 1. We just end up with the sum between I equals 1 and infinity of di cos beta I x over L equals 1. Well, as we did with the Fourier series, we now multiply both sides by cos beta j x over L and integrate from minus L to plus L. As before, we can then reverse the order of the summation and the integration, so which is what I've done in going from this line to this line, and then you can show in the same way that I did for the Fourier series in an earlier lecture that the value of this integral is equal to 0 if I is not equal to j. So the integral only is non-zero if I equals j, and this basically gives us a way of selecting di and working out the value of di. So if I does equal j, then this is what we've got overall. So just doing the integration and evaluating between the limits minus L and plus L, when we work that through we end up with that di equals 4 sine beta I over 2 beta I plus sine of 2 beta I. So in other words, our overall solution is theta equals the sum from 1 to infinity of this 4 sine beta I over 2 beta I plus sine of 2 beta I times the exponent of minus beta I squared alpha t over L squared times the cos of beta I x over L, where each of the beta i's are given by the root of the equation that beta sine beta equals the bio number. And that clearly means that the values of the beta I are not entirely trivial to obtain. Now, applying that temperature distribution, for the case of the bio number equals 0.1, the normalized temperature distribution through the plate looks like this for two different values of alpha T over L squared, namely 1 or 10. So you can see that the distribution is essentially got a parabolic form, and obviously it goes to lower dimensionless temperatures as the time increases. Although the overall solution is a series solution, in practice it turns out that the first term of the series is usually dominant, and if alpha T over L squared, which is actually given the special name of the Fourier number, is greater than 0.2, then using only the first term of the series will give a result that is better than 99% accurate. And this was recognised a long time ago, and the solution summarised on that basis in a graphical form to give what is conventionally known as the Heisler chart. So the x-axis of this chart is alpha T over L squared. The y-axis is the dimensionless temperature, in this case the dimensionless centerline temperature, hence the subscript C. And each of these lines corresponds to different values of K over HL, or in other words different values of 1 over the bio number. You'll notice that the graph stops at the left hand end at the point that alpha T over L squared equals 0.2. In other words, additional terms would have been required to get extra accuracy here, although in fact you'll see that in terms of this graph all the lines would have been so bunched together you wouldn't have been able to read them. The first term also works for temperatures not on the centre line, so if alpha T over L squared is greater than 0.2, then the dimensionless temperature is equal to 4 sine beta 1 over 2 beta 1 plus sine of 2 beta 1 times the exponent of minus beta 1 squared alpha T over L squared times cos of beta 1 x over L. Thus, if you're at the surface temperature theta s equals the centerline temperature times cos of beta 1, because x over L equals 1, and all the other terms are identical. And this graph summarises the temperatures at different depths in terms of the centerline temperature. So the y-axis is the temperature at a given depth divided by the centerline temperature theta c versus K over HL, and each of the lines corresponds to a different depth. So x over L equals 1 is of course the surface, and as you work up the way you're going inwards. Of course, although there isn't actually a line drawn here, if you went straight along at the top you would actually be plotting the centerline temperature. So we have two different graphs, one of which looks at the centerline temperature and the other which looks at temperatures at different depths related to the centerline temperature. If we now consider the case of the aluminium strip discussed earlier, 1 over beta I in this case turns out to be 3100. That's not on any of the charts that we're dealing with. That means the bio number equals 3.23 times 10 to the minus 4. But of course we can work through things fully mathematically, and in this case it turns out for that value of the bio number, the value of beta 1 is 0.0179596. For time of 10 seconds, alpha T over L squared is 84.4. So putting all this together gives us the expression for the dimensionless temperature shown here, and hence this centerline dimensionless temperature theta c equals 0.973183, dimensionless surface temperature equals 0.973026, and these are clearly very similar numbers, and that's reflected in the actual temperatures, which are 195.17 and 195.14 degrees centigrade respectively. And this of course just reflects the high thermal conductivity of the aluminium alloy, and shows that in this particular case the additional complications introduced by trying to find the temperature gradients have not really been worth the effort, because we basically got this answer from the lumped solution. However, in other cases this approach will be worth the effort. And for next time I'd like you to do a calculation using a Heisler chart for a large slab of carbon steel which is initially at 425 centigrade and the slab is 0.15 meters thick, suddenly cooled at the surface by air at temperature 16 centigrade, convective heat transfer coefficient of 20 watts per meter squared per Kelvin, and I would like you to calculate the centre and surface temperatures of the slab after 2 hours of cooling, given the thermal conductivity is 43.3 watts per meter per Kelvin and the thermal diffusivity is 1.21 times 10 to the minus 5 meters squared per second. Overall, therefore, today I've looked at a model of strip casting, first of all in terms of the lump solution, and then a way of getting the temperature gradients inside the strip using a Heisler chart solution, and also the fact that this Heisler chart solution, it basically summarizes a series solution, but as long as alpha t over L squared is greater than 0.2, the first term of that series solution is sufficient to give you 99% accuracy. Thank you.